Hi, in this video I want to talk about this Carmichael's Totient function conjecture. Now, I hope we all know what totient function is, which I'll represent it like this, totient of alpha. Totient function basically gives you the amount of integers that is up to alpha minus 1 that are co-prime to alpha. So if, like, let's say, totient of 8 is equals to 4. Why? Well, because 1, 3, 5, 7 are co-prime to 8. 2, 4, 8, they all have the GCD of 2. So that's basically what totient function is. And now, this is obviously a conjecture, and well, I obviously don't have any solution to this, but I have some ideas that I've found that we can use. Now, first of all, this conjecture says that for every n, there exists and such that totient of m equals to totient of n. So this is basically the conjecture. It looks so straightforward, but it is hard to prove. Now we can see that totient of, let's say totient table 1, 2, 3, 4, 5, 6, 7. Totient of 1 is 1. Totient of 2 is 1. Totient of 3 is 2. Totient of 4 is 2. Totient of 5 is 4. Totient of 6 is 2. Totient of 7 is 6. Now what we can see is for totient of prime, this is gonna be p minus 1, which that actually makes sense because like if we have 7, all the numbers up to 7 are gonna be co-prime to it. So I think that kind of makes sense to write p minus 1. Well, and we can obviously see that we have pairs. We don't have any pairs for 4 and 6 yet, but if we just write more values, 8, 4, see these two pair up, and somewhere 6 is also gonna pair up with some value, and there is this one formula to find totient of a value. So let's say, what is totient of p to the k? Well, this actually needs some proof, but like in this video, I'm not gonna prove this, and I'm sure there are proofs of this out there. And if you guys want, I can actually make a video proving this. And this is gonna be p to the k minus p to the k minus 1, which is gonna be equals to p to the k minus 1, p minus 1. And we also assume that we also know this knowledge too. So totient of yeah, alpha beta equals to totient of alpha times totient of beta for greatest common divisor, which I'll shorten it GCD of alpha and beta equals to 1. I'm also assuming we know this knowledge too. If requested, as I said, I can also prove this in other videos. Now then, here is what I found. Now we can represent every number as either even or odd, right? Let's take odd values. 1, 3, 5, 7, it goes on, right? Now realize that none of these odd values are gonna be like, when you take 2, right, and an odd value, their greatest common divisor is gonna be equals to 1. Because like 2 is a prime, right? And none of these odd values include 2, so their GCD is gonna be equals to 1. So for a given odd value, let's say mm, for odd alpha, this is alpha, we can say totient of alpha equals to 1 times totient of alpha, right? Equals to, we can see that from our table, totient of 2 is equals to 1, which we can then replace it as totient of 2 times totient of alpha. Because alpha is odd, we can say this is equal to totient of 2 alpha. So basically, for odd values, we can just multiply it by 2, and we can see that our theorem is satisfied, right? Our conjecture is satisfied. And yeah, this is the easy part. And what about even values, you might say? If alpha can be written as, let's say, 2 beta for beta odd, then we can say totient of um, alpha equals to totient of beta, right? So for even values, let me make a line here. If our value is only divisible by 2, then we can add, like, we can factor the beta out to satisfy our conjecture. So this brings us to alpha equals to 2 to the 2 to the c times, or let me write, yeah, to the c uh times d for c greater than 1 or greater than or equals to 2, let's say, right? Because if c is equals to 1, then we can easily divide it by 2 to get beta. If c is equals to 0, well, we can just multiply by 2 to get the same value. Now yep, this is where I have developed this conjecture, and from here things get tricky. Well, for obvious reasons, assuming d is odd, like assuming we factor all the 2's out, then we can say totient of alpha is equals to totient of 2 to the c times d is equals to totient of 2 to the c times totient of d equals to 2 to the c minus 1 times 1, which we can omit, totient of d. So this comes from here, if some of you guys are wondering. Yeah, we found this, great, but from here we basically cannot find anything. Like, this is the endpoint for me. I couldn't just enhance it, and I also wanted to share what I found in this conjecture about this conjecture. Maybe some of you guys might solve it. Like, just try it out. So that's basically all for this video. I hope you guys enjoyed it. If you have any question, please leave a comment and have a great day.